Welcome back and welcome to the last lesson of linear relations. So today we're going to be looking at writing equations and graphing linear relations. So in the first example here, we have to consider the pattern. Each small square has a side length of 1 centimeter. So we have 1, 2, 3, and 4 figures that we're going to be looking at for different rectangles that we're going to be looking at made up of square tiles. For the table here, we're going to be looking at the rectangle number, which is listed above, and the perimeter. Remember that each side length of the square was 1 centimeter. So for figure 1, we have 1, 2, 3, 4, 5, 6 centimeters for a perimeter. For figure 2, we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 centimeters. For figure 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We have 10. So already you can start to see a pattern happening. Our rate of change for the rectangle number is 1. Our rate of change for the perimeter is 2. It's increasing by 2 every time. So we would figure that for rectangle 4, we're going to have a perimeter of 12. Well, let's see if that's true. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So yes, our rate of change stayed consistent here, and from here to here, we had a change of 2. So, in words, what are we noticing about the rectangle number and the perimeter? Well, as the rectangle number increases by 1, our perimeter is increasing by 2. The next thing it's asking for is in the equation, in an equation. The next thing it's asking for is in an equation. So in a formula, what is this going to look like? Well, remember that finding our constant was important to writing our formula or our equation. So if we had 0, if we worked our way backwards, instead of adding 2 this time, we're taking away 2. So our constant is going to be 4. Now that'll help us writing our equation because our constant is going to be plus 4. Now what are we calculating? Well, we're looking at calculating our perimeter. So perimeter equals, and our rectangle number is represented by an n, and this is where our rate of change comes in. Well, our rate of change, we already know that the rate of change on the perimeter is 2, and our rate of change on the the rectangle number is 1. So it would be 2 over 1. Or you could write P equals 2n plus 4. Both would be correct. The next thing that it's asking for us to do is use the equation to determine the perimeter of a rectangle number 12. So if we had the figure number 12 of the rectangle, what would our total perimeter be? Well, n in this situation is 12. Our formula or our equation that we are going to use is P equals 2n plus 4. Now for the n, we know that we're going to input a 12 for the figure number. P equals 2 times 12 is 24 plus 4. P equals 24 plus 4, makes 28. So that is our perimeter for a figure number, or the rectangle number of 12. Don't forget, our unit is centimeters. Now it's saying the rectangle number with a perimeter of 40 centimeters. So this time we know that P equals 40 centimeters, and we're going to be working backwards. So same equation, P equals 2n plus 4. Now because we know that P is going to be 40 centimeters, we're going to substitute that in for P equals 2n plus 4. Now we have to move this 4 over, so you do that to both sides. You do the opposite. It was adding, so we're doing subtraction. That gives us 36 equals 2n. Now in order to get n by itself, we have to divide by 2. Divide by 2, that cancels. And you're going to have 18 equals n. Now 18 is going to be your figure number. Next, we're going to take this information even further and we're going to plot this on the graph. Now pay attention, it says do not connect the points. This is discrete data. Remember, you can't have a partial figure, so you can't have a partial rectangle, so it's only going to be plotted on the exact points and we're not going to be connecting those dots. But in order to do this, we have to plot our points and we have to figure out what is going to fit on our graph. Well, we have to get up to figure number 4 because that's what we went on to with the table earlier. So we need to fit 4 across the bottom. If I just go every 2, I'm going to fit that on there. 1, 2, 3, 4. Now it is important to also label your graph. So when we're labeling the graph, we have to look at, well, what were we putting across the bottom here? On the bottom, it is our rectangle number. So our rectangle number is on the bottom. Now up the side, what we're going to be putting is our perimeter in centimeters. Now we got to figure out, what do we have to go up to? Well, if we look back at that table that we made, our highest value here is 4 and 12. So we have to get up to 12. If I go every 2 again, this should fit. So 2, 4, 6, 8, 10, and 12. Perfect. It's going to fit on this graph. So now we've labeled our y and our x axis. We've made the graph so it's going to fit. We chose appropriate values. Our next thing to do is plot the information. So when we looked at rectangle number 1, we had a perimeter of 6. That's where our first point goes. When we had rectangle 2, it had a perimeter of 8. When we had rectangle 3, perimeter of 10, and 4 was 12. Now remember, we are not connecting these dots. So this is where you would stop for this. For the above example, the perimeter is affected by how many rectangles there are. So the perimeter depends on the number of rectangles. So we say that the x depends on the y. So P is the dependent variable and n is the independent variable. the dependent variable goes on the y, so the vertical, and the independent variable goes on the x, and that's going to be your horizontal. And that's the case for all graphs. The above graph gave a straight line, so if it gives a straight line, we know that it created a linear relation. In the relation above, the constant change of 1 in the number of rectangles, n, produced a constant change of 2 in the perimeter, p. And we know that's true because of the table that we looked at, because of the words that we wrote out describing the table and the equation, and we also know that's true because of the graph that we created. So we took everything that we've learned through this whole unit and we're putting it all together now. In example 2, it says graph the linear relation of the table of values. So we're going to look at the number of DVDs rented, which is going to be D, and the cost, which is going to be C. Now, is our number of DVDs going to be independent or dependent? Well, this is going to be our independent variable, leaving our cost to be our dependent variable. Now, the cost, so the amount you're going to pay, is all dependent on how many DVDs you're actually getting. So that's why it's called your dependent variable. It depends on how many you're actually buying. When we're looking at our number of DVDs, we also want to look at what's our rate of change. Well, it's increasing by +1, increasing by +1, and third one, just to make sure, increasing by +1. For our cost, well, it's going from $3.50 to $7. So if you did $7 subtract $3.50, you would find that you increased by $3.50. From $7 to $10.50, again, it's an increase of $3.50. And your third one, just to make sure it's a linear relation, is again $3.50. Part A says to graph the data, and the second part to that says, does it make sense to join the points on the graph? Explain. Well, if we're thinking about buying DVDs, you have to think, can you buy part of a DVD? Well, if you can't buy part of it, or you can't break that down any further, then it doesn't make sense. So no would be our first part, and then because it says explain, well, the data is discrete. We cannot buy a portion of a DVD. There are no possible values between the points on the graph. So there's no reason to connect the dots because there's going to be no way of getting that value. So just like we did on the last page, we have to set up our graph so that we can fit our values in here. Now remember that we decided that our independent variable is going to be our number of DVDs. So that's going to go across the bottom. So our number of DVDs, and we have up to 5 DVDs that we're looking at. So if I go 1, 2, 3, 4, and 5, we can fit all the points in there. Now we have to do our y-axis as well, and on our y we decided that our dependent variable is going to be our cost, and our cost is measured in dollars. And for our y-axis, we have to get up to a value of $17.50. So if I make every line $2, I should be able to fit everything on here. So I got up to 20 there, so we know it's going to fit on here. Our last thing that we need to do is plot the points. When we had our first DVD, it cost $3.50. So I'll go back to my graph. The first one, well, 3 would fall right in the middle. So we're going to assume it's halfway in between that. So 3/4 of the way up that line. So our first point is going to go right there. Our second DVD is going to bring us up to $7. So at DVD 2, we move up, and 7 is going to be found right in the middle. For 3, we're at a cost of $10.50, which will bring us here. That's a quarter way up in between 10 and 12. Then we have 4 DVDs, which brings us to $14. And 5 DVDs will bring us up to $17.50. Now we aren't connecting these dots, but we should realize that it should look like a linear relation. It should be creating that straight line, and if any of the plotted points are way off from where they should be, double check to make sure that you put that down in the correct spot. Part B here says, is the relation linear? Well, yes, we just talked about it. It's creating that straight line, and that is how we know. So yes, the data forms a straight line on the graph. Now, that isn't the only reason you know that the relation is linear. You also know the relation is linear because the rate of change in the table is consistent. Part C asks, use the table to describe the pattern in the rental cost. How is this pattern shown in the graph? Well, as the number of DVDs increases by 1, the cost increases by $3.50. We also see this on the graph going from one point to the next, and it's creating that staircase. So if we looked at this, it's creating an equal staircase every time. It's going to move by the same amount every time. Moving on to example 3, it says solving problems using a linear relation. In the first question here, it says the student council is planning to hold a dance. The profit in dollars is 4 times the number of students who attend, minus 200 for the cost of the music. Write an equation that relates the profit to the number of students who attend. So we have to come up with the equation that we're going to use to help solve for the following questions. Now, before we can do that, we have to think about what information was given to us. Well, it says the profit in dollars is 4 times the number of students, and it is minus 200. Actually, we don't even need all that. Minus 200. So your minus 200 is going to be telling you what your initial value was. So your initial value equals $200. So it's negative $200 that you had to pay for that music. And the profit in dollars is 4 times the number of students. So your rate of change is going to be 4 over 1. So now that we have our initial value, which would be like our constant, and our rate of change, we can create this equation. So y equals our 4 times the profit, and our number of students is going to be X, and our initial value, so our constant there, is $200. That initial value is not changing, so how much we paid for the music is always going to be $200. So just to make sure we have this labeled down, our number of people is going to be X, and our cost is going to be Y. Now we have to look at creating this table. Well, if we had 0 people show up, we lost $200. If we had 10 people show up, well, let's put this information into our formula and we'll see what we get. Y equals 4x subtract 200. Y equals 4 times 10 subtract 200. Y equals 4 times 10 is 40, subtract 200. So y would equal negative 160. So we still haven't made a profit with 10 people, but we've reduced how much we've lost. Next part would be, well, what if we went up to 20, and then 30, 40, 50, and 60. So let's look at what 20 would be. Same formula comes over. This time we're just inputting for X. We're putting 20 in there. Subtract 200. Y equals 80. Subtract 200. Y equals 120. So our value here now is negative 120. Negative 120. For 30, same formula comes across. Y equals 4 times 30, subtract 200. Y equals 120, subtract 200. Y equals negative 80. So now we're at negative $80. Now, because I know I'm working with linear relations, I could save myself some time here. If I wanted, I could keep doing the formula over and over again to find my data. But I could also look at what's my pattern here, what's my rate of change. Well, here we're increasing by 10 every time. So increasing by 10 every time. On my cost, my rate of change for cost is $40 every time, because I went from 200 or negative 200 to negative 160, negative 160 to negative 120, and so on. So if that pattern is going to follow down, I'm going from negative 80 plus 40 will make negative $40. Negative 40 will bring me to 0, and now at 60 people I have made a profit finally. So 50 people is that magic number where I've broken even, but where I actually turn a profit would be 51 people. Part C here says to graph the data in the table. Does it make sense to join the points? Now I'm going to leave this for you to finish off here because I want you to make sure you're understanding the way to set up a graph, how to lay out a graph and choose a value that's going to fit in the graph, and if you should be or should not be connecting the dots. Once you have checked your answers in the class OneNote, we're going to move on to example 4, which is writing an equation to represent an oral pattern. So Jeffrey has $130 in his savings account. Each week he withdraws $20. Write an equation that relates the amount of money in his account. A is going to be dollars and T is going to be weeks. Now, looking at the information that they've given us, Jeffrey has $130 in his savings account. Now, this is going to be our constant. So that's our initial value that he has in there. And each week, so whenever there's something that's changing, which is the weeks in this situation, this is going to tell us our rate of change. So $20 is our rate of change. Now with that information, we can put together an equation to solve for the amount of money. Now the amount of money in this equation is represented by A, and our weeks is represented by T. So each week he withdraws. Now if you withdraw money, you are taking money out of your account. So you are taking out $20 every week, which will be a T in this situation, plus $130 because that's how much Jeffrey had at the start of this. So he has $130 every week. He is withdrawing, so taking out $20 from his account, and it's going to decrease how much money he has left in his bank account. Part B says, create a table of values for the relation, then graph the relation. Now looking at 0 for a time, well, if we use A equals negative 20 t plus 130, well, if you put in 0 for your t plus $130, that makes A equals 0 plus 130. A equals $130. So at the beginning, we knew he had $130. Next, we want to figure out how much he's going to have in his account after 1 week. So A equals negative 20. And this time for T, we're putting in 1 plus 130. A equals negative 20 plus 130. A equals $110. So $110. Now our rate of change, which we already knew, but we just double checked by doing the formula, was negative $20. So every week he's losing $20. From 110 to 90 is again a rate of change of negative 20, and so on. You're going to go 70, 50, and 30. So at 5 weeks, he is down to $30 in his account. Moving over to the graph, now we have to plot this information. So at 0 weeks, he has $130. At 1 week, 110. At 2 weeks, 90. 3 weeks, 70. And you can see the linear relation that it is creating. Part C says, will you join the points on the graph? Well, are you going to have part of a week when he's withdrawing money? Well, he's only withdrawing every week. So we won't be withdrawing partway through the week. So no, we will not be joining the points because Jeffrey does not withdraw money partway through the week. Part D now says, at what point will Jeffrey have $50 in his account? Well, if we look back up at the graph here, we're looking for $50. Well, $50 is going to be right there. So we're looking at week 4 is when he'll be down to $50. We could have also looked at the table and week 4 would tell us that information. If we didn't have the table or the graph, we could have used our equation to calculate for that answer. The last question here, which is technically example 5, is writing an equation to represent an oral pattern. So this is exactly what we just did, and I'm going to leave this one for you to complete on your own to check your understanding. And that brings us to the end of linear relations. So if you have any questions about the concepts that we've covered, or the material, or just any general questions, please make sure you email me and I'll get back to you right away.